Let us continue to question 19. Question 19 says, find the smallest positive integer n so that each digit of 15 times n is 0 or 8. Okay, so what does this mean? It means that 15 times n, 15n in other words, it has only zeros and eights, right? And you want the smallest value for n. Okay, well, in the first instance, such a number will be divisible by 5, so therefore it will end in 0. It ends in either 0 or 8. It can't end in 8, so it ends in 0. So you got the last number. Then such a number is also divisible by 3, so that if you add all the digits, you're going to get to 24. I'm sorry, you're going to get a multiple of 3. Now, the sums which will, the digits which will contribute towards the sum are the eighths. And the smallest number of eighths that you can create is 888. 888 is 24, the sum, and so that's divisible by 3. And this whole number here, ending in 0, is divisible by 15, and that's the number you're looking for. With 888, yeah, this is the only way in which you can write 3 eighths. Okay, so this is equal to 15 times n, which gives the smallest n, right? And then when you divide this by 15, you get 592. So question 19, the answer to question 19 is 592. Okay, this is a strange problem at this level, because these problems at this level are very difficult. Okay, let's just check to see. Yeah, there it is, 592. Okay, let's go and get on to question 20, which says the following. You've got in the figure ABCD is a regular pentagon. So you got A. So the pentagon is this A, B, C, D, and E. Okay. And then you got some 8 symbols, yeah? So this is a regular octagon, starting from A, T. You can see it, A, T, comes down like that, like that, like that. From here, it goes up to this, like that, like that, like that. So that's a regular octagon. So you got 2 regular pictures. Regular polygons are polygons which have got equal sides and equal angles. All right. And you also know that the sum of the exterior angles of any polygon is 360 degrees. And I hope you know that. So for a pentagon, if you want to calculate the interior angle of a pentagon, a regular pentagon, well, the exterior angle, the 5 exterior angles, it's a pentagon, 5 exterior angles. They sum up to 360 degrees. And they're all equal because it's a regular. The interior angles are all equal, so the exterior angles will also be equal. So the interior angles will be 180 minus that. This is 180 minus 72, which is 108 degrees. And the interior angle of a regular octagon in the same way, the, the, the exterior angles will always add up to 360 degrees, but this has got now 8 sides, 8 angles. So all the exterior angles are all equal. They'll be equal to 360 over 8. And the interior angle will be 180 minus that. That's 180 minus 45, which is 135 degrees. I needed that. The reason for that is I'm going to calculate if at some point x here, with x on CD and C on WX. All right, so the point is you need to calculate this angle here, ZAB. This angle here. Right, let's call this X. Okay, what I'm going to do is to calculate this. I know the interior angles of the pentagon and the octagon. This part here from here to here is an interior angle of the pentagon. So let's call this angle here Y, the small angle. Call the small angle Z. Right? X is your unknown. So we do know that X plus Y, X plus Y is equal to an interior angle of the pentagon, which is 108 degrees. And we also know that X plus Z X plus Z, that becomes an interior angle of the octagon, which is 135 degrees. (135). Okay. Now we know all the other angles, T, U, W, B, W, all these angles. And we've got an outside figure which has got 1, 2, 3, 4, this outside one. So this 5, 6, 7. So this outside polygon has got 7 angles in it. The sum of the 7 angles is the sum of the interior angles of any polygon. Okay, the sum of the interior angles of any polygon having n sides is n minus 2 straight angles. So let's just rewrite this neatly. STRAIGHT. Okay. You see, if you've got a triangle, the sum of the angles of a triangle is 3 minus 2 straight angles. That's one straight angle. A straight angle is 180 degrees. Right? So in a triangle, it's 3 minus 2 times 180. Quadrilateral, it'll be 4 minus 2 straight angles, which is 2 times 180, which is 360. like that. So this is 5 straight angles, and 5 times 180 is 900 degrees. All right, so let's add up all these angles. I'm going to add, we'll put a square around the octagonal angles. Now this angle here is also an octagonal angle. But this one is a pentagonal angle, the circles. All right. So when you add up all these things, you got 1, 2, 3, 4. 4 times 135. Those 4 angles. And the other 3 angles are this D plus E. These are 108 degrees. And then you have this X plus Y plus Z. But this angle here, this large angle, is X plus Y plus Z. And that we just saw is 900 degrees. So we don't have enough space here. This is 540 plus 216, that's 756. So you'll see that X plus Y plus Z is 144. I'm going to put it, so X plus Y plus Z, $144. Okay, so we need to calculate X, remember. So we have X plus Y is 108. And so we can work on Z here. See, X plus Y is 108. So Z must be 36. I'm going to just take this thing out from here to create some space. Now we got X plus Y plus Z is 144. So Z is equal to 36. I don't want Z. Oh, okay, I do want Z. So now X will be 135 minus 36, and that is 99. So that is what we needed, X. So the answer to the problem is 99 degrees. Okay, the prerequisites for this are the sum of the angles of any polygon is n minus 2 straight angles. The sum of the exterior angles is always 360 degrees, no matter how many sides there are. And if it's regular, all the exterior angles are equal, which allows you to calculate all the equal interior angles, which we have done. Okay, so let's clear these drawings and see what we have done here. Oh, we came to this answer very quickly, 99 degrees. So maybe you can have a look at that to see why we came so quickly. Maybe I didn't explain anything nicely. All right, so let's get on to the next problem. It's problem number 21. Problem 21, I found this to be a rather difficult problem. You see, the first 2 elements in a sequence of hollow cubes. Now, you've got the diagrams of two cubes here. This is a cube. It's hollow. All the stuff has been taken out from the inside, but you've also got holes on the sides. So constructed from small cubes according to the pattern are shown in these figures. The first element, for example, is made up of 44 small cubes. Now you can count them. I can see, I don't know whether you can see it, but there are five little cubes on this side, five this side, five this side. So these little holes here, in this case, it's got three. One, two, three. One, two, three. It's 3 by 3 hole here. And the 6 faces of the cubes each have got 3 by 3 holes. So in figure 1, let's just analyze figure 1. That itself is rather complicated. Figure 1. Okay, you've got 6 holes. You have 6 holes, and just hold on, please. Sorry about that. I had to switch my phone off. Okay, you got 6 holes. Um, what else do you have? It's got how many? So each of the holes is a 3 by 3. And so all these holes are 3 by 3 holes. It says it, the number of 3 by 3 holes. It means 9 little cubes have been taken out from those sides. Right? And it's a hollow cube. So how do you calculate how many um, cubes there are in this picture? Well, in figure 1, you've got, let's take figure 1. Imagine this thing was filled up with all these cubes. It's a solid cube. Then you will have 5 cubed, 5 cubed uh, little cubes inside that. But it's a hollow cube, so the inside has been removed. The inside is the hollow part. You got 5 on the outside, so it will be 3 cubed. 5 cubed minus 3 cubed, because the inside, the hollow part is a 3 by 3 by 3, right? You got this side here and this side here come out, and you'll have only 3 sides in the thing. But over and above that, the 6 holes, each one has got 9 cubes. Those holes have also been removed in addition to the cube, the hollow cube inside this. So what is this? It's 125 minus, and this is 27 plus 54 is 81. There we have it. So it is 44. So this is made up of 44 small cubes. Right. So this calculation allows us to calculate at any level. But just watch. In figure one, you got six holes. In figure two, you see you have one hole on the side. Here, in the second figure, you got two squared holes each side. Right? And in figure three, you'll have three squared holes on each side. It'll be 3 by 3. You see, this is 1 by 1, and this is 3 by 3 in the similar figure, and so on. So the number of holes is 3 squared. So in figure n, you'll have n squared holes. Okay. And they will uh, account for each of those n squared holes, the n squared holes on each side. It's important. On each of the 6 sides. So there are they account for 6n squared if you count all the 6 sides of this cube. And each of those holes have got 9 little tiles. So these are 6n squared holes. So this gives you 54n squared. Now what I'm doing here is counting the amount of holes, cubes which have been removed. And this 54n squared equals the number of cubes, small cubes, removed from the sides. To make 6n squared holes. In each side there's n squared holes. Okay, so now if you want to count in figure n, you see what they say here is that if the pattern continues, what is the total number of 3 by 3 holes that the element constructed? So if you know 674 cubes were used to make up the faces, how big is this cube? See? So we just calculated this 44 is the number of cubes that were used to make up the very first figure. Right? And in the nth figure, figure n, what have you got? You've got, now this 5, let's have a look at the number of the size of the first figure. It's this 5, where is it coming from? Sides. In 1, you've got 5. The second figure, if you count all these, you've got 9 here. You've got 9. Actually, it is 2 times 3 plus 3. Because these 3 here, and you got 3 bars. That makes 9. And in the third figure, you will have 3 times 3, which is 9, plus 4, which is 13. Right, so in the nth figure, the number of sides will be 4n plus 1. You can see 4 times 1 plus 1, 4 times 2 plus 1, 4 times 3 plus 1. Okay, so it's 4n plus 1 in the nth figure. So that's the number of cubes on the side. So the solid cube will have 4n plus 1 cubes, solid. Now you remove the whole, the inside hole, and the inside hole you have to just reduce that by 2, right, to create the hollow. So you reduce this by 2, it will be 4n minus 1 all cubed. This is very similar to this. 5 cubed minus 3 cubed. We had to remove 2 on the edges to get the inside cube. So now this is the, the solid cube minus the hollow. So this gives you the whole surface here. But the surface, we must still remove these 54n squared. 54n squared small cubes which are removed from the sides, right, to make the holes. So now we have to calculate this thing here. All right. I should have created some space here, which I didn't. Anyway, let me create some space at the top. To make this calculation, you see. I got a thing to calculate here. So this is 4n plus 1 all cubed minus 4n minus 1 all cubed minus 54n squared. This is the total number of cubes that are used to construct a thing of side or in the nth figure, So this is the difference of 2 cubes. And you can factorize the difference of 2 cubes. It's 4n plus 1 minus 4n minus 1. It's a minus b, a cubed minus b cubed. It's a minus b into a squared. That's 4n plus 1 all squared. A squared plus ab. So plus the product of these two. Well, I can see what the product is. It's 4n plus 1 into 4n minus 1. It's a difference of 2 squares. So it's 16n squared minus 1. 4n all squared minus 1. And then plus the square of the last one. A minus b into a squared plus ab plus b squared. That's just the factorization of these two. And I must still subtract from that 54n squared. Okay, now here the 4n and the 4n cancels off, and you're left with 2 there. And here, let's expand all these things. You've got squaring 4n plus 1, 16n squared, plus 8n, plus 1, plus 16n squared, minus 1. And here you have 16n squared, but minus 8n, plus 1. Okay, and you're still subtracting 54n squared from that. So 8n minus 8n cancels off. 16n squared, 16n squared, 16n squared. 3 16n squared, that's 48n squared, but times 2. So it's 96n squared. And then the plus 1, minus 1, there's still a 1 here which survives, plus 2. 2 times 1. Then you take away this 54n squared. And that gives you 42n squared plus 2. Right? 96 minus 54 is 42n squared plus 2. And you see it fits in very nicely because n is figure 1. When n equals 1, you get 44. All right, so this rather complex calculation seems to be, we are in the right track because we checked it for the first figure and it works. And now we are told that the number of cubes in the nth figure, whatever the n is 674. So we've got that this thing here, 42n squared plus 2 is equal to 674. I'm sorry, 42. So 42n squared, 672. If you divide 672 by 42, you get 16, which is very nice, which means that n is equal to 4. So by the time you come to the fourth figure, you've got 674 cubes. The question here is, if the pattern continues, what is the total number of 3 by 3 holes that the element constructed will have on its faces? So the number, we're still not at the end of this. The number of 3 by 3 holes equals, we saw that on each face that there were n squared holes, but there are 6 faces, so it's 6n squared, and n is equal to 4. So the answer is 96. The question is the number of holes. 96 holes in the figure, which has got 674 small cubes constructed, which are used to construct it. Okay, as you can see, it's a very intense problem. It's problem number 21. The answer is 96. So there it is, a long essay here, but you can see at the end of it is 96. So if you didn't follow what I said, you can read this again and consolidate it. It's a, let's see, this problem 21. Problem 22. A point P is 9 units from the center of a circle of radius 15. So let's see now. This looks like a nice, easy problem. Let's draw a circle. Oh, at least I discovered something. Okay, so you've got a circle and you've got a point P is inside this. It's 9 units from the center. Let me just make this thing a little bit bigger. Yeah, that looks more like a circle. Um, so you have the center. Point P is 9 units, and the radius of this circle is given. It's 15. The radius is 15, and your point P is 9 units from the center. So when you join these two, you get 9. That distance is 9. The radius is 15. Okay, now they ask how many chords of the circle, including the diameter, pass through P, having integer lengths. All right. And this is the background to this thing here. Just remember the radius is 15 and it's 9 units from the center. And I'm going to just remove all these guys here. Now, there's your point P. And you've got a number of infinitely many chords that go through this thing. A whole lot of chords. But the question is, how many chords have integer lengths? So amongst all these chords, you have a diameter. See, I could have the diameter which goes through the center. And that's the largest chord, right? So the largest chord is the diameter. Let me see whether I can use that effectively. So if the diameter is the largest chord, remember the distance from P to this is 9. The radius is 15. So the distance from here to here is 15. So the distance from here to here is 15, but this part is 9. So let me just remove this. Yeah, sorry. So the radius from center to the boundary is 15, and therefore the remaining piece there should be 6 here. Because this is the center. All the radii are equal. Okay, so the longest chord is 30. And any chord, all chords have length less than or equal to 30, because the diameter is the longest chord. So we'll just hold on to that. Then you also see that you can't, these chords here, they can't be too small. I can't have a chord that length, for instance. So the interesting question is, what is the minimal uh, chord, the length, what is the minimal length it can have? Okay. There's another chord which is perpendicular to this diameter. This is the point P. I could draw a chord which is perpendicular to the diameter. What is the length of that chord? Well, we know that when you go from the center, if you drop a line perpendicular, these two will be equal. And that's one of the theorems in geometry. So these two will be equal. The reason is that if you join those endpoints, okay, now the radius here is 15. This is 9. This is perpendicular. So you got a right angle triangle here. It's 9, 15, and if you calculate it, you'll see that this part is 12. But since from the center, if you drop a perpendicular to a chord, it bisects the chord. So you got this chord here has got length 24. right? It turns out that this is the shortest chord that you can draw. Any other chord will be longer than 24, right? But now we have to prove that. How do you prove that this is the shortest chord? The diameter, okay, that's fine. All chords have got diameter is the longest chord. But how do you know that the shortest chord that you can go through P is the one that is perpendicular to the diameter that goes through P? Right, now for that, now we need a little bit of geometry. And I'm going to go to this first picture here. There's your point P. You take any two chords that go through P. A, B, and C, D are random chords. And there's a very beautiful theorem in geometry, which you don't do in school, which says that when you take any two chords that go through P, then P divides each of those chords into two pieces. It turns out that the products of these pieces is always the same. We draw a chord here, this product is the same as the product of those two pieces. Remarkable result, right? It's called, it's associated with a subject in geometry called the power of a point. No matter which chord you take, the power of P is equal to this constant number, AB. It doesn't really matter which one. So in particular, if you take the chord which goes to the diameter, you can actually calculate what this constant is in terms of the radius. Maybe you can research that. You'll find it's in some geometry book, or you can even find it in my book, The Power of a Point. It's called The Power of a Point. I just spoke about briefly about my book. It's a book which is sold by the South African Maths Foundation, SAMF, www.samf, South African Maths Foundation, .ac.za. And is it at, I don't know, .ac.za. And it's called 1000 Mathematics Olympiad Problems. You've got a lot of um, various types of problems there, all Olympiad type, with the solutions and with the notes and everything. And amongst the notes, you will find a whole section on power of a point. Okay, if you go to the site here, you'll be able to get all the information about this book. It's quite a big book. It's got 643 pages, but it's quite a gold mine of ideas which are used in Olympiads, especially the lessons. I think we've got over 200 pages of lessons there. And amongst those lessons, you've got the power of a point. Okay, let's just get back to this. To prove this is quite easy because you see, these two triangles here are similar. Why? Because AB or AD is a chord and it subtends equal angles at C and B and C, angles in the same segment. So these two angles are equal. Vertically opposite angles are equal. So two of these angles here are equal to two angles of the angles here. So therefore all three angles will be the same, right? So they are similar, which means that the sides are in proportion, right? Which now you take the side A in this triangle, it's opposite theta. So the side opposite theta in this triangle, which is similar to it, is D. So that proportion will be the same as you take this side in this small triangle, it's opposite the remaining angle, C, and here the remaining angle is that, so it's over B. And so you get A over D is equal to C over B, cross multiply, bingo, AB is equal to CD. Okay, so that's just an aside there, uh, because we can use that twice. Remember, I've got so if I take a suppose P is a random point, right? Like this. So AB, and now yeah, you got P is this, we're going to our problem. This point here is 9 units away from this is 9 units, right? So if you look at the perpendicular one, you'll see that this product here, AP times PD, in this case here, AP times PB, we saw that it was 12 already, but if you use this method here, you'll see that AP times PB will be the same as 6 times 24. 6 times 24. If you take the chord which is perpendicular to AB at P, right? And this is 144, but AP and PB are equal if this is perpendicular. So therefore, the both of them are 12. So earlier on we calculated 12 by using Pythagoras. Okay. Now, there's another result in in algebra, which is called the what is it called? The arithmetic AG or something like that, inequality. Not sure exactly what that is. Inequality, which says that for any real numbers, for any two positive numbers, x and y, you'll always have that the average of the two numbers is greater or equal to what you call the geometric mean, which is the square root of the product. Right? You always have that. So in this case here, if I take AB, the square root of AB, right, yeah, is less than or equal to A plus B over 2. Right? So therefore, A plus B is greater or equal to 2 times square root of AB. But AB, AB is equal to any product that goes through this thing. And we saw that the one that goes through the diameter from P, right, it has got 6 times 24. So this is 2 times square root of 144. That's 24. See? And that's 12 plus 12. Remember, I said that the sum of these two, the length of this chord, so AB, the length of the chord, the random chord through your point P is greater or equal to 24. I said earlier on, I'm going to prove that this 24 is the smallest possible sum that you can get. All right. So this took a little while, but to do this, you use to get the AG inequality, right? And this too, if you want to check it out, you can look at my book and you will get more information on that. Right. Okay, so in short, what we've got is that any chord for any AB, any chord AB containing P, the point P, which is chosen to be 9 units away from the center, the length of the chord is between 24 and 30. We saw the diameter is 30. Now we want integer values. So 24 is integer, 30 is integer. The question originally is, what are the integer, how many integer lengths do you have, of these chords? In a circle, if you just draw any chord, it can have any value. But we want to have it to be a positive integer. How many are there? So now the number of integers here is 24, 25, 26, 27, 28, 29, 30. Let me just pause here. You see, if I got a point P here, the smallest chord, the smallest length is that, 24. Now, I can get 25 by just rotating this thing around P slowly. I can come to a length which is 25. And continue to rotate it, you'll come to 26. And continue until you come to the diameter, which is 30. And if you keep rotating, you'll see you're getting chords which are smaller than 30. So all these are attainable. That's the point. We have chords which have got length 25, 26, 27, 28. Now, the one which has got, for instance, if this length here was 25, then if you take your diameter, right? And if you reflect this thing on this side, there will be another one with length 25. See? So you got, if there's one length chord of length 25, there's another one which is symmetrically across the diameter. So there are two of length 25, the same with all these, there are two of these, but with the diameter, there's only one. When you reflect the diameter across itself, you get nothing. And yet to the perpendicular one, when you reflect this thing across the diameter, you'll get the same thing. So this will produce only one chord. The 30 will produce one chord, but all the others will produce two. So the number of such chords if you add up all these, is 12. It looks easy, this problem, but it's a very difficult problem, um, like many of these. For those of you who are listening, you are learning quite a lot. because you can see um, how deep the solutions are, and you've got a lot of ideas on how to solve them. Okay, so we are only at problem. Let's just remove all these diagrams and go to the next thing. And you see right at the bottom, I've got all these arguments here. You'll see the answer is 12. So I'm exposing this so that, and it's recorded. And when you look at the recording, you'll be able to pause here and read that and get some better idea of how to understand this problem. Okay, so the next problem that we have is 23. It says that if A, B, and C are distinct positive integers, all right, they are counting numbers, 1, 2, 3, 4, 5, and so on, such that, oh my God, you got some complicated looking thing here. Find the value of A plus B plus B, C. This looks decidedly difficult, very difficult problem. But this object here is actually an interesting object, the one in the left-hand side. The product of all the three, and then you've got all the possible products of two at a time, and here one at a time. Okay. This kind of thing occurs here. If I multiply 1 plus A times 1 plus B times 1 plus C, right? Don't ask me where I got that from, but this comes with experience. So you got 1 plus A, you multiply these two, I have 1 plus A plus B plus AB into 1 plus C. So you have this whole thing here times 1. Right? And this whole thing times C. So multiply every one of them by C. I'm multiplying each of these by C. C times 1, C. C times A, AC, and so on. And you notice that this part here, A plus B plus C, there it is. AB, AC, BC, and ABC. So this entire thing is 1,000. So this product is 1,001. So given this, that this product is 1,001, and 1,001, when you try to factorize it, you'll see 7 goes into this. 7 goes into this 143 times. And then if you continue to factor, 1 plus 3 is 4. So this is 11 goes into this. That's the rule for divisibility by 11. So you got that this products of these three numbers is also 7 times 11 times 13. Let me just remove all this for the time being. Well, not for the time being, permanently. Okay, so now does this mean now that we know what A, B, and C are? Not necessarily. You got the product of three numbers is the product of these three numbers. But there's, okay. So you could have other factors for this, you see. You could have 1 as a factor, 1 times 7 times 143, right? 3 numbers being multiplied. But if one of these is 1, then one of these is 1, which means that A, B, or C is 0. If any one of them is 1, and they say they are positive, see? So none of these is 1. Because if any one of them was 1, that particular one will be 0. So you don't have this possibility. So this is the only possibility. But now you'll say, okay, how do I know what A is? You got 1 plus A is equal to 7 or 11 or 11 or 13, which means that A is equal to 6 or 10 or 12. See? So which one is it? Actually, it doesn't really matter because A plus B plus C, if you turn these things around, whether it's B plus A plus C or C plus A plus B, you will always get the same sum, right? So the numbers A, B, and C will be 6, 10, and 12. Right? A, B, C, 6, 10, and 12. And whether whatever these permutations there are, A, B, C will always, A plus B plus C will always be 6 plus 10 plus 12. And that is 28. So the answer to this problem is 28. And the trick here was to recognize that this thing here is connected to this product. See, that is the thing about mathematics, higher mathematics or problem solving. Over the years, you pick up a lot of little facts. And you have to just remember these little facts because they come in to be quite useful in problems. So if you go through all these problems that are in these various um, um, recordings that I'm making, I think I'm making over 50 recordings. So if you go and check those problems, you'll get a lot of information which will help you to solve problems of very high quality. Okay, so let's just take this thing out and check to see the same answer. You got A plus B plus C is 28. So we go to question 24. Question 24 says f is defined on the set of integers and satisfies, it's got a funny rule here. F of n, if n is greater or equal to 1,000, so let's just look at the first one. If n is equal to 1,000, these are integers, so 1,000, 1,001, 1,002, and so on, then f of n, you simply subtract 3 from that. So f of n will be equal to n minus 3. Right? Like the f of 1,000 will be 997, 998, 999, and so on. Right? But if n is smaller, if n is any one of the numbers from 1, 2, 3 up to 999, that is n less than 1,000, it's an integer, then f of n is given by this funny thing here. It's f of f again of n plus 5. All right. And the question is find f of 25. Now, 25 is right at the bottom, very far away from 1,000. Let's just start with f of 1,000. Is 997. Because this includes n to be 1,000. So if n is 1,000, then it's 1,000 minus 3. But I want to see f of 999. I might be able to get that because you see, you're going to increase this n by 5, and that will take it across 1,000. And 999 is less than 1,000. I can't use that rule anymore. But this is f of double f of 999, the same 999 here that occurs here. You add 5 to it. Right, so it is. So inside here you got f of 1004. But this one we can calculate it because this is more than 1,000. So this is f of 1001. F of 1004 is 1004 minus 3. Now this is still greater than 1,000. So f of this is 998. 1001 minus 3. So we're able to calculate f of 999. Like that, you can try 998, the same kind of a thing. But this time, when you add 5 to it, it's 1003. And then f of 1003 is f of 1,000. And it comes to 997. Right. It looks as if we've reached the end of the line because f of 1,000 is that's only one we know. But let's continue. Let's try f 997. Well, not quite. Yeah. Yeah. F of 997 is what? This is f of 997 plus 5 is 1,002. The f of 1,002 is 999. But we've calculated f of 999. So this is 998. We just calculated it. And like that, f of 997, 996 will be f of 1001. Because you keep adding 5. And that is f of, this is 998. And we calculated f of 998 also, there's 997. So you have the strange thing that the image, we call it the image, or the value at 998, 997, they seem to be just jumping from 998 to 997. So we can conjecture that when n is odd, the value is 998, and when n is even, it's 997. There's odd here 998, even 997. But we don't know. The thing may just break down somewhere. But it looks like the answer is f of 25, which is the odd number. It looks as if it's going to be 998. So that is what we expect the answer to be. But there is a hole in this problem. So we don't know whether this pattern will continue. Now there is a thing called mathematical induction, which allows you to prove that this pattern continues. Right? I'm going to let's take, for instance, now, let's take, suppose I want to find out what is f of 46. Right? And suppose I've calculated all the ones above, and we know Oh, f of 46. Knowing that f of odd, f of odd is 998 for odd numbers bigger than 46. And f of even is 997 for even numbers greater or equal to 46. In other words, I'm coming down, right? And I come up right up to 46 now. Is it going to work? And I know it's working right through. When I say working, that the rule that f of odd is 998 and f of even is 997, it comes all the way. And now we want to check whether f of 46 is actually 998. No, not greater. It's greater than 46. So we don't know whether f of 46 is going to be 997. We don't know that, right? So let's do it. So you got f of 46. I'm going to prove that f of 46 is 997. What is this? This is equal to f of, and we got this 26, 46. You add 5 to it, you get 51. Now we already checked that for odd numbers bigger than 46, the f, the formula worked. So the the odd numbers will become 998. So this is 998. And f of 998 we saw was 997. So for this even number here, it comes to 997. You see, just assuming only that it's true for all numbers bigger than 46. And if you try 45, you'll see that the same kind of calculation will lead to 998 again. So if it's true for all the above, it's also true for these. And then if you keep coming down like that, you will see that, in fact, instead of 25, for 46, I should have taken 25. I took f of 25. And then knowing that for all the others, it works. I hope you understand that. This is the principle of mathematical induction. Um, it is a rather, and in this particular case, it's uh, it's a difficult application. But when you do it uh, normally, it's a very easy principle to apply. Okay, so let's just take this thing off and ask ourselves. So you see the f of 25 is 998. And again, the thing is proven for that. So you can check the proof of this. And using that page, the last page, read it carefully and then try to understand exactly how that is proved. You might be able to get a better understanding of mathematical induction. Now this looks like a frightening geometry problem. The squares A, B, C, D this is A, B, C, D. All these are squares. No, this one here, E, F, G, H, K, L, M, N, P, Q, R, C. All these are squares. Now, how are they constructed? You're starting off with A, B, C, D. You take a point E on AD. Just focus on this A, B, C, D, the original one. Right? Join it to C. And then on this line, you construct the square. When you construct the square, this thing intersects and it goes up to this point here, right? You got a square. And remember, you're starting with E as a midpoint of the side. So now you do the same thing with this square here. On this line here, you draw a square. Then you take the midpoint of this. No, actually, not a midpoint. You see where it intersects. Where it intersects this line here, K, you draw a square, right? And then on this square here, you take the midpoint. This is the midpoint here. And you go up to that, like that. And the question is, what is the value of LQ squared? Frightening, very frightening problem. And what I'm going to do is, I'm going to just analyze just the first two steps from A, B, C, D to E, F, G, C. And I'd like to simply calculate this length here. I'd like to calculate that length. They do tell you that the length of CD is 8. So the original square has got side 8. I'm not going to bother about that for the moment. Um, I want to calculate AF. And I need only these two squares. So I've drawn the diagrams. So you can see in the first diagram, I want to calculate AF. For a start, I'm going to say, suppose the side length is 4A. Later on, you'll see why, because then I'm going to try to avoid fractions, right? And if I make it A, then I'm going to have fractions, or X, I'll have fractions. I don't want fractions. 4A is nice. Now, we started off by saying that E is the midpoint of this. So each of these is 2A, right? And then we drew a square on this. So this is 90 degrees here. Like that, we drew a square, this is 90 degrees. And then this thing, it cut this thing at some point K. It goes up to that. Now, I claim that K is the midpoint of EF. You see, E is the midpoint of AD. At the starting point, E is the midpoint of this side here. And then this construction is made. And if I know that K is the midpoint of EF, then I'm doing exactly the same thing that I did on the original one. Because now I join that, as you can see, and then construct the square on that, come down like that, right? And go up to where this point is. Here it goes up to L, right? And if I can calculate FA in terms of AD, then I'll be able to calculate FL in terms of FE because it's the same construction, but on a different square, right? So we'll just use that. So that is why I need to calculate FA. Right, and the calculation of FA is not very easy. Now watch. I'm going to use this diagram here. See, because I've got a 90 degree here, these two angles, they add up to 90 degrees. But these two angles also add up to 90 degrees. So this angle and that angle are the same, which allows me to say that these two triangles, the small triangle and this triangle, are similar because they've got the same angles, theta 90 and something else. So if they are similar, the sides are in the same ratio, right? So the side opposite theta, for instance, okay, let's look at this one here. AK. The side opposite theta in the small triangle, AK, over the side opposite theta here is 2A. It's similar triangles, right? Is the same as if you take the side opposite this other angle there, which is 2A, and the side opposite this remaining angle there, which is 4A. Ah, but this is half, right? So AK is a half of 2A. So AK must be A, right? For it to cancel. So that is why I've got AK is actually A here. So this part here is really A. Right. Now, you'll see I've drawn some other lines here. I'm going to remove this calculation. I'll come to the situation where AK is A. Now, I've created a new point G, which is the midpoint of AB. See, I've got 4A here. So G, this part here will be 2A. So G is 2A this side and 2A this side. So you'll have an A there like that. See? So both of them. AK will be equal to KG because AG will be 2A, you see. GB is 2A. The whole thing is 4A. So AG, and I just said that AK is A, so this will also be A. Now, I now claim that EK is equal to KF. That's a claim. And to do that, I'm going to do this EK over KF. No, EK over EF. I want to prove that EK is half of EF. And that'll mean that EK and KF are the same thing. So EK over EF is EK over EF. If you remember, we constructed a square here. Is the same as EC. EF is the same as EC. But now you'll see that I'm looking at these two. EK is the hypotenuse of this triangle. EC is hypotenuse of this triangle. And we said that those two triangles are similar. So this hypotenuse over hypotenuse will be equal to the ratio of the other two sides. So it'll be 2A over 4A. All these sides are in the same proportion. That's a result in similar triangles. If the two triangles have the same angles, then the sides are in the same proportion. The ratios of the sides are all the same, the three ratios. Oh, this is a half. See? So that means that EK is a half of EF. And that means that these two are equal. Right? I'm trying to calculate AF. Still a long way from that. Now, I join AG, and I have an interesting figure here. AFGE, we got that this EK is equal to KF, and we got AK is equal to AG, because we said that earlier. So it means that these two diagonals, they bisect each other in this quadrilateral. And in any quadrilateral where the diagonals bisect each other is a theorem in geometry, it means that that quadrilateral is a parallelogram. Only for parallelograms, the diagonals bisect each other, and conversely, if the diagonals bisect each other, it has to be a parallelogram, which means that AF is parallel to EG. Not only that, AF is actually equal to it. So you have that AF. I'm going to calculate AF squared because the question was to find LQ squared. We're still very far away from that. We're going to get to LQ squared. So I'm going to calculate AF squared. So AF squared is equal to EG squared. The EG squared, EG is the hypotenuse of this triangle here. EAG. So it's EA squared plus AG squared. It's a right angle triangle. And EA squared, we said that is 2A all squared. And AG, by construction, G was the midpoint of this. That's also 4A squared. So you have 8A squared. So AF, we calculated AF squared, right? But I'd like to know how is AF related to the original square that we had? And the original square, the area of that original square is 4A squared. So this is half of 4A all squared. It's a half of 16A squared, and 4A is AD. All right, so this is where we are. We are at this stage here. That AF squared is equal to half of AD squared. AF squared is half of the original square which created AF, right? That length there, the square of that is half the side of the square. See? Okay, so what does this mean? It means now, if I do the same process for the new square, the second square, which is F that, right? Remember, we started by doing this. taking the midpoint of a side, joining it to this, constructing the square and landing at that point, right? And that point, we calculated the square of its distance from this vertex. I'm going to do the same thing here. The new square. There it is. This is the midpoint. Remember, we proved that this is the midpoint here in this. This is the midpoint. So now you construct the square on that, and this is LF squared we can calculate. LF squared in exactly the same way as previously is half of FE squared. See? But we're not really interested in LF squared. We're interested in LQ squared. So you'll have that LQ squared. Now that is the third square. Yeah, from the midpoint here, you go up to this and do that, and then calculate LQ squared. LQ squared will be a half of KL squared. I am not drawing the square that created Q. It's too complicated here. But in the original diagram, they have done it. We'll go back to that just now. So this is half of KF squared. Now KF, no, I'm sorry, it's KL squared. LQ squared is half of KL squared. But KL and KC are the same thing. So it's half of KC squared. Now KC squared is this squared plus this squared. So it's half of KE squared plus EC squared. Because this KC squared, KL, same as this because this is a square here. And this squared by Pythagoras is that squared plus that squared. And this is half of. Now KE squared, that's the hypotenuse of this triangle. Remember, this was A here. So that's 4A squared plus A squared. Right? We showed that there was A there. So that is KE squared. And EC squared is the hypotenuse of this triangle, which is 4A squared plus 16A squared. And now you have 16, 17, 25A squared. So this is a half of 25A squared. Right, so LQ squared we've calculated in terms of A. And remember, they told you that the original length was 8 here. I said ignore that information. 4A is equal to 8. So therefore A equals 2. We are using A equals 2 the first time here because it's very much easier to use symbols than to use numbers. You can do algebra with symbols. So the answer is A equals 2. So this is a half of 100. 2 squared is 4. So LQ squared is 50. All this. Okay. And let's just go back to our original question. The LQ squared is 50. You see, there's your LQ. They've actually drawn all these squares. That is why this thing is so complicated. I didn't draw this last one. I just put the Q here. Right? But if you did draw the last one, you'll get this picture. And the question is, what is the value of LQ squared? So And there it is. You see the last thing is LQ squared is 50. Okay. Now, actually, I'm going to show you all these. This is a picture that we had. Now, you can stop at this freeze, this pane here, and check all these things out. And you will see I still get LQ squared equals from here. Then I got another method of calculating. To prove that EK equals KF was very crucial. And I had various ways. You can drop a perpendicular here and do that. It's a very nice geometry here. So this also allows you to prove that EK equals KF. And then I got another one here as well, a third method. And here I use trigonometry, right? Rather very complex calculations. And eventually you come to the same thing, that AF squared is half AD squared. Most important thing is that AF squared is half of AD squared. And I can prove that using trig, right? And using the cosine formula. Okay, I'm not going to discuss that because I found much better proofs. And that this was my original proof, which I was very unhappy about. Okay, so that brings us to the end of 25 and the end of South African Maths Olympiad Senior Round 2, which was set in 2025. Thank you very much for listening.